Okay, so this is lecture number 8 in business statistics course. Hopefully it's going to be relatively short because what we need to discuss in this part of the lecture is the special type of normal distribution. So in previous lecture number 7 we looked at the just general normal distribution, and I told you that the normal distribution is probably one of the most popular or widely used distributions, and it is for a good reason that we're going to actually discuss in the next chapter. So in this lecture what I wanted to discuss is something that's called standard normal distribution. So let me first of all kind of point out that, let me go back to the one of the previous slides that we had. Yeah, right there. Okay, so even this one. We discussed that in order to get the shape and the position of the normal distribution, you need to specify two numbers, two values, and that is the mean, the location of the peak, and also standard deviation, how wide, the measure of how wide is the distribution. So as long as you specify these two numbers, mean and standard deviation, you pretty much know everything about normal distribution. Now, how many different means, what are the different values that the mean can take? Can the mean be positive? Sure. For example, we can assume that the heights of humans are normally distributed. Well, approximately normally distributed, right? Let's say that the average height is, I don't know, 5'7", for example, okay? And standard deviation, let's say 3 inches, okay? So if you collect a bunch of observations, measure a lot of human heights, then you can probably, that's what I'm guessing, you will get the line which is approximately normally distributed. Okay, so mean in that case is positive. The average height is 5'7", for example. Okay, can mean be negative? Yes, it can. For example, let's say we're talking about temperature in Antarctica. Okay, I seriously doubt that the temperatures in Antarctica ever rises above 0. So therefore, the average temperature throughout the year, average daily temperature, is probably negative. Okay, so mean, there is no limit on what values the mean can take. It can be a positive number, it can be a negative number, it can be any number really. Are there any restrictions on standard deviation sigma? Well, yes, actually there are restrictions. Sigma can take any values, but it can, as long as its value is the value is positive, it cannot be negative. And the reason is very simple. It's the measure of the width, right, of the distribution. So how can the width of the distribution be negative? That doesn't make much sense. And if you remember how standard deviation is computed, it's simply square root from the variance, right? Square root is a positive value. Well, it can be negative, of course, right? If you take square root from number 4, the answer is plus or minus 2. But since sigma is the measure of the width of the distribution, it can take only positive values. So anything above 0 is all possibilities for sigma. So therefore, in the world, out there, in the real life scenarios, there can be infinite number of possible means, and just the same, infinite number of possible standard deviations. Okay, so in the pre-computers era, before we had Excel, or even before Excel, when we had calculators or big mainframe computers, statistics still existed. The idea of normal distribution was actually introduced, I believe it was in 18th century, could be 19th century. And normal distribution, by the way, here is another kind of piece of trivia. Sometimes it's also called Gaussian distribution. Gaussian, in honor of the German mathematician Karl Gauss, who I believe lived in the 18th century. So his contribution to the different branches of mathematics were so big that Normal distribution was also named Gaussian in his honor. So in the pre-computer era, statisticians still had to deal with normal distribution with different probabilities. Now, since you don't have access to the computers, how can you calculate different probabilities? Do you have to tabulate every possible value of every possible normal distribution with different means and different sigmas? There are infinitely many of them, right? How do you do that? Well, statisticians developed the following trick. Okay, they have decided at one point in time that out of all possible values of the mean and all possible infinite number of values for the standard deviation, let's settle on the two. For the mean, it's the value of 0, and for the standard deviation, it's the value of 1. So if you have normal distribution that looks like this, where the average is 0, and the standard deviation, which is kind of measure of how wide it is equal to 1, then in this case we're going to call that normal distribution standard normal. Where is that? Standard normal distribution. Okay, so special case, 0 is the mean, standard deviation is 1. As it turns out, any normal distribution can be converted into the standard normal by the following simple trick. This is something that's called standardization. Okay, so you may heard about that. You may covered that material. May have covered this material in Math 125. It's something that's called calculating the z-score. Right. So the z-score. So if x is normally distributed like this, okay, so it's bell-shaped normal distribution with just any mean, mu can be any number, and any sigma can be any number. And if you take the random variable x, subtract mean from that, and divide that by sigma, then you're going to convert that standard, that normal distribution into the standard normal. So you can imagine that to be done in two steps. First step is when you subtract from every possible value of the random variable x, when you subtract its mean, it's as if you're moving the peak to 0, right? Because, for example, this point right here, okay, the point of the peak of the mode. The location of this point, x equals mu, the mean, right? When you subtract mu minus mu, you get 0. So therefore, the first step, when you take x, normally distributed, and subtract mean, you're simply moving the entire curve to be centered around 0. And the second step, when you divide by sigma, essentially what you're doing is you're changing the shape of the distribution. Okay, so if it was very narrow, so sigma was small, when you divide by small number, you're getting larger numbers, right? So therefore, the tails of the distribution are becoming more, well, more bushy, so to speak, right? So the distribution is getting more spread to the right and to the left. On the other hand, if sigma was high, therefore your distribution was relatively flat and spread far on the right and on the left. And by dividing your x variable by sigma, which is greater than 1, you're kind of moving points down, so therefore you're getting it less flat, you're getting it more concentrated, right? So in other words, when you divide your x minus mu by sigma, you're going to change the shape, and the shape is going to be exactly normal again. Mean is 0 because we moved it to the 0, and then we changed how wide or flat the distribution is by dividing by sigma. Okay, so this step again is called calculating the z-score or standardization. Okay, so our previous problem, if you remember, we discussed Dell computers, right? Assembling laptops, desktops, servers, what have you, any kind of computer equipment. And the times are normally distributed with the mean of 50 right here and the standard deviation of 10. So this is how different times to assemble computers are distributed. And I believe we calculated this probability that a randomly selected machine takes anywhere between 45 to 60 minutes to assemble. And we just basically used p-norm function in our studio, right? So we calculated the area to the left from 60 by using p norm, and subtracted the area to the left from 45, again using another p norm function, and the difference was the area from 45 to 60. Okay, so what I'm going to do right now is calculate the same exact value. If I remember correctly, it was the probability was 0.53 something something. 0.53 is what I remember. I don't remember decimals. Okay, so I'm going to calculate exactly the same number by converting into the standard normal distribution from just normal with a mean of 50 and standard deviation of 10. So here's what I'm going to do. From each, so here's my inequality. X is between 45 and 60, right? I subtract, so I'm going to perform that transformation. So in the middle here, I'm going to move from X, the normally distributed variable with a mean of 50, into Z, the standard normal variable. So the first step is to subtract the mean mu from all parts of this inequality. X minus mu, 45 minus mu, that's minus 50, that is minus 5 right here, and 60 minus mu, that's 60 minus 50, that's 10 right here, right? And then divide by sigma. So here in the middle I have exactly Z, right? But I remember that sigma is 10. So on the left side, 45 minus 50, that's minus 5 over 10, that's minus 1/2, minus 0.5. And on the right side, I have 60 minus 50, that's 10 over 10, that's 1. So therefore, the same thing, probability that the X normally distributed is between 45 to 60 minutes, is the same exact thing as to ask what is the probability that a standard normal Z, so now it has nothing to do with the original problem, right? Apparently, it's just about Z, some variable which is distributed as standard normal. Okay, so it's not time anymore; it's a Z, standard normal. The value of Z is between minus 0.5 to 1. Okay, so let me go ahead and do the same exact problem using RStudio. Okay. So I believe it was actually in the first example, right? Time to assemble the computer is normally distributed with a mean of 50, sigma 10. Yeah, okay. So here is where we computed the probability that it's between 45 to 60 minutes, right? So we subtracted probability p norm to the left from 60 minus p norm to the left from 45, and the answer was, let me run this line again, right there, 0.5328. And now what I'm going to do is calculate the same number alternatively, right? Alternatively, as we discussed, it is probability that a random variable Z, right here, Z, is between negative 0.5 and positive 1. I'm gonna say plus 1. Okay, so it's p norm, right? So I'm going to use the same idea. P norm to the right from upper level, to the left from upper boundary, minus p norm to the left of the lower boundary. So p norm to the right, to the left from upper boundary is 1, right? Right here, my upper limit is 1. Okay, mean is what? For the standard normal, we know that the mean is 0, and the standard deviation SD is 1. And the fact that I'm looking in the left tail, lower tail equals true. So it's everything to the left from 1 minus everything to the left from lower boundary, which is minus 0.5. So same function p norm. Okay, and the value is negative 0.5. Mean is 0. Standard deviation is 1. And I'm looking in the left tail, so lower tail is also true. So numerically I should get the same value. Well, let's see. Ta-da! It is the same. So I can compute the same probability in two different ways. I can just use my actual distribution, normal with a mean of 50 and sigma 10, or I can convert that into the normal, into the standard normal z. In this case, lower limit 45 becomes negative 0.5 for z-score, right? So negative 0.5 is the z-score for the value of 45. And the z-score for the value 60 is 1. So z between minus 0.5 and 1 gives me exactly the same numerical answer. So this is how essentially, the point of the story is, this is how probabilities were computed in the pre-computer era. So mathematicians really created a big, gigantic table where they tabulated in a very detailed way the area under the standard normal distribution, under the z distribution, for all kinds of different possible values of z. And after that, they could convert that into, they could convert any problem about any normal distribution with any mean and any sigma into the problem about z only. So that was kind of their workaround, or the trick, how to compute normal probabilities without having access to the computer firepower that wasn't available until computers were invented somewhere in the middle of 1940s, 1950s. Okay. All right. So and similarly, so let's take a look. I have another one, a couple of slides. So this is going to be a relatively short lecture, right? Very similarly, how we computed the values given the area under the curve, we can do exactly the same thing for the standard normal distribution without changing much of anything, right? So the only difference really between standard normal and any other normal is that standard normal has the average of 0 and sigma of 1. So if I have standard normal right here, and the area in the right tail is equal to some number a, whatever that can be, 0.05, 0.025, 0.1, whatever, then I can find the z value that cuts off the area A in the right tail by using the same thing that we did before, that is Q norm function. Q for quantile, norm for the normal distribution. But for example, just to give it a kind of practical spin, right? What if I have the value in the right tail equals to 2.5%, 0.25, right? In terms of proportions, 2.5% is 0.025. So let me go ahead and find the z value that gives me 2.5% in the right tail. So in other words, I'm gonna switch over to RStudio right here. Right? Okay, find a value, z value, right? Not just any value, z value that gives area 0.025 in the right tail. In other words, using my standard notations, I'm looking for the z with the subscript 0.025, right? Okay, so Q norm, and the area is 0.025. The mean is 0. Standard normal always has the mean of 0, and SD, standard deviation, is 1. And lower tail, is that true? No, I'm looking in the right tail, so therefore this is false. Okay, and when I run that line, here it is. I'm gonna give it a couple of enters. So z value, so z right here, I'm gonna type it. Okay, z with a subscript 0.025. Give it a pound sign, right? This is comment, this is not really a command. Equals to 1.9599, or roughly speaking 1.96. Okay, so that concludes our discussion of the standard normal distribution and normal distribution just in general. And in the next lecture, we are going to actually take a look at why exactly normal distribution is so famous among statisticians. Why is it so special? Okay, and it's actually a pretty interesting phenomenon which is called central limit theorem. So I'm going to stop this lecture right here. It was the short one, and in the next part we're going to discuss central limit theorem.